This chapter covers generation of the minimal data input for a test case, comparison of the output of a function with the expected output, guidance about the quality and the quantity of the test cases. In a data-oriented system, our code deals mainly with data manipulation. Most of our functions receive data and return data. As a consequence, it's quite easy to write unit tests to check whether our code behaves as expected. A unit test is made of test cases that generate data input and compare the data output of the function with the expected data output. In this chapter, we write unit tests for the queries and mutations that we wrote in the previous chapters. Section 6.1. The simplicity of data-oriented test cases. Theo and Joe are seated around a large wooden table in a corner of La Vie est Belle, a nice little French coffee shop located near the Golden Gate Bridge. Theo orders a café au lait with a croissant, and Joe orders a tight espresso with a pain au chocolat. Instead of the usual general discussions about programming and life when they're out of the office, Joe leads the discussion towards a very concrete topic: unit tests. Theo asks Joe for an explanation. Theo, are unit tests such a simple topic that we can tackle it here in a coffee shop? Joe, unit tests in general, no, but unit tests for data-oriented code, yes. Theo, why does that make a difference? Joe, the vast majority of the code base of a data-oriented system deals with data manipulation. Theo, yeah, I noticed that almost all of the functions we wrote so far receive data and return data. Tip. Most of the code in a data-oriented system deals with data manipulation. Joe, writing a test case for functions that deal with data is only about generating data input and expected output, and comparing the output of the function with the expected output. The steps of a test case. 1. Generate data input, data in. 2. Generate expected output, data out. 3. Compare the output of the function with the expected output, f of data in and data out. Theo, that's it? Joe, yes. As you'll see in a moment, in DOP there's usually no need for mock functions. Theo, I understand how to compare primitive values like strings or numbers, but I'm not sure how I would compare data collections like maps. Joe, you compare field by field. Theo, recursively? Joe, yes. Theo, oh no, I'm not able to write any recursive code in a coffee shop. I need the calm of my office for that kind of stuff. Joe, don't worry. In DOP, data is represented in a generic way. There is a generic function in Lodash called _.isEqual for recursive comparison of data collections. It works with both maps and arrays. Joe opens his laptop. He is able to convince Theo by executing a few code snippets with _.isEqual to compare an equal data collection with a non-equal one. Theo, nice. Joe, most of the test cases in DOP follow this pattern. Theo decides he wants to try this out. He fires up his laptop and types a few lines of pseudocode. Tip. It's straightforward to write unit tests for code that deals with data manipulation. Theo, indeed, this looks like something we can tackle in a coffee shop. Section 6.2. Unit tests for data manipulation code. A waiter in an elegant bow tie brings Theo his croissant and Joe his pain au chocolat. The two friends momentarily interrupt their discussion to savor their French pastries. When they're done, they ask the waiter to bring them their drinks. Meanwhile, they resume the discussion. Joe, do you remember the code flow of the implementation of the search query? Theo, let me look again at the code that implements the search query. Theo brings up the implementation of the search query on his laptop. Noticing that Joe is chewing on his nails again, he quickly checks out the code. Section 6.2.1. The tree of function calls. The waiter brings Theo his café au lait and Joe his tight espresso. They continue their discussion while enjoying their coffees. Joe, before writing a unit test for a code flow, I find it useful to visualize the tree of function calls of the code flow. Theo, what do you mean by a tree of function calls? Joe, here, I'll draw the tree of function calls for the library.searchbooksbytitle JSON code flow. Joe puts down his espresso and takes a napkin from the dispenser. He carefully places it flat on the table and starts to draw. When he is done, he shows the illustration to Theo. See figure 6.1. Theo, nice! Can you teach me how to draw a tree of function calls like that? Joe, sure. The root of the tree is the name of the function for which you draw the tree. In our case, library.searchbooksbytitle JSON. The children of a node in the tree are the names of the functions called by the function. For example, if you look again at the code for library.searchbooksbytitle JSON, listing 6.4, you'll see that it calls catalog.searchbooksbytitle_.get and json.stringify. Theo, how long would I continue to recursively expand the tree? Joe, you continue until you reach a function that doesn't belong to the code base of your application. Those nodes are the leaves of our tree. For example, the functions from Lodash, _.get, _.map, and so forth. Theo, what if the code of a function doesn't call any other functions? Joe, a function that doesn't call any other function would be a leaf in the tree. Theo, what about functions that are called inside anonymous functions like catalog.bookinfo? Joe, catalog.bookinfo appears in the code of catalog.searchbooksbytitle. Therefore, it is considered to be a child node of catalog.searchbooksbytitle. The fact that it is nested inside an anonymous function is not relevant in the context of the tree of function calls. Note: a tree of function calls for a function f is a tree where the root is f and the children of a node g in the tree are the functions called by g. The leaves of the tree are functions that are not part of the code base of the application. These are functions that don't call any other functions. Theo, it's very cool to visualize my code as a tree, but I don't see how it relates to unit tests. Joe, the tree of function calls guides us about the quality and the quantity of test cases we should write. Theo, how? Joe, you'll see in a moment. Section 6.2.2 Unit Tests for Functions Down the Tree. Joe, let's start from the function that appears in the deepest node of our tree, catalog.authornames. Take a look at the code for catalog.authornames and tell me what are the input and the output of catalog.authornames. Joe turns his laptop so Theo can get a closer look at the code. Theo takes a sip of his café au lait as he looks over what's on Joe's laptop. Theo, the input of catalog.authornames is catalog data and author IDs. The output is author names. Joe, would you do me a favor and express it visually? Theo, sure. It's Theo's turn to grab a napkin. He draws a small rectangle with 2 inward arrows and 1 outward arrow, as in figure 6.2. Joe, excellent! Now, how many combinations of input would you include in the unit test for catalog.authornames? Theo, let me see. Theo reaches for another napkin. This time he creates a table to gather his thoughts. Table 6.1. Theo, to begin with, I would have a catalog data with 2 author IDs and call catalog.authornames with 3 arguments, an empty array, an array with a single author ID, and an array with 2 author IDs. Joe, how would you generate the catalog data? Theo, exactly as we generated it before. Turning to his laptop, Theo writes the code for catalog data. He shows it to Joe. Joe, you could use your big catalog data map for the unit test, but you could also use a smaller map in the context of catalog.authornames. You can get rid of the Books by ISBN field of the catalog data and the Book ISBNs field of the authors. Joe deletes a few lines from catalog data and gets a much smaller map. He shows the revision to Theo. Theo, wait a minute, this catalog data is not valid. Joe, in DOP, data validity depends on the context. In the context of library.searchBooksByTitle.json and catalog.searchBooksByTitle, the minimal version of catalog data is indeed not valid. However, in the context of catalog.bookinfo and catalog.authornames, it is perfectly valid. The reason is that those two functions access only the authors by ID field of catalog data. Tip: the validity of the data depends on the context. Theo, why is it better to use a minimal version of the data in a test case? Joe, for a very simple reason. The smaller the data, the easier it is to manipulate. Tip: the smaller the data, the easier it is to manipulate. Theo, I'll appreciate that when I write the unit tests. Joe, definitely. One last thing before we start coding. How would you check that the output of catalog.authornames is as expected? Theo, I would check that the value returned by catalog.authornames is an array with the expected author names. Joe, how would you handle the array comparison? Theo, let me think. I want to compare by value, not by reference. I guess I'll have to check that the array is of the expected size and then check member by member recursively. Joe, that's too much of a mental burden when you're in a coffee shop. As I showed you earlier, see listing 6.1, we can recursively compare two data collections by value with _.isEqual from Lodash. Tip: we can compare the output and the expected output of our functions with _.isEqual. Theo, sounds good. Let me write the test cases. Theo starts typing on his laptop. After a few minutes, he has some test cases for catalog.authornames, each made from a function call to catalog.authornames wrapped in _.isEqual. Joe, well done. Can you think of more test cases? Theo, yes. There are test cases where the author ID doesn't appear in the catalog data, and test cases with empty catalog data. With minimal catalog data and _.isEqual, it's really easy to write lots of test cases. Theo really enjoys this challenge. He creates a few more test cases to present to Joe. Theo, how do I run these unit tests? Joe, you use your preferred test framework. Note: we don't deal here with test runners and test frameworks. We deal only with the logic of the test cases. Section 6.2.3 Unit Tests for Nodes in the Tree. Theo, I'm curious to see what unit tests for an upper node in the tree of function calls look like. Joe, sure. Let's write a unit test for catalog.bookinfo. How many test cases would you have for catalog.bookinfo? Theo takes another look at the code for catalog.bookinfo on his laptop. Then, reaching for another napkin, he draws a diagram of its input and output. See figure 6.3. Theo, I would have a similar number of test cases for catalog.authornames, a book with a single author, with two authors, with existing authors, with non-existent authors, with... Joe, whoa, that's not necessary. Given that we have already written unit tests for catalog.authornames, we don't need to check all the cases again. We simply need to write a minimal test case to confirm that the code works. Tip: when we write a unit test for a function, we assume that the functions called by this function are covered by unit tests and work as expected. It significantly reduces the quantity of test cases in our unit tests. Theo, that makes sense. Joe, how would you write a minimal test case for catalog.bookinfo? Theo once again takes a look at the code for catalog.bookinfo. See listing 6.10. Now he can answer Joe's question. Theo, I would use the same catalog data as for catalog.authornames and a book record. I'd test that the function behaves as expected by comparing its return value with a book info record using _.isEqual. Here, let me show you. It takes Theo a bit more time to write the unit test. The reason is that the input and the output of catalog.authorNames are both records. Dealing with a record is more complex than dealing with an array of strings, as it was the case for catalog.authorNames. Theo appreciates the fact that _.isEqual saves him from writing code that compares the two maps property by property. When he's through, he shows the result to Joe and takes a napkin to wipe his forehead. Joe: Perfect! Now, how would you compare the kind of unit tests for catalog.bookinfo with the unit tests for catalog.authorNames? Theo: On the one hand, there is only a single test case in the unit test for catalog.bookinfo. On the other hand, the data involved in the test case is more complex than the data involved in the test cases for catalog.authorNames. Joe: Exactly. Functions that appear in a deep node in the tree of function calls tend to require more test cases, but the data involved in the test cases is less complex. Tip: Functions that appear in a lower level in the tree of function calls tend to involve less complex data than functions that appear in a higher level in the tree. See Table 6.2. Section 6.3. Unit tests for queries. In the previous section, we saw how to write unit tests for utility functions like catalog.bookinfo and catalog.authorNames. Now we are going to see how to write unit tests for the nodes of a query tree of function calls that are close to the root of the tree. Joe: Theo, how would you write a unit test for the code of the entry point of the search query? To recall the particulars, Theo checks the code for library.searchBooksByTitleJSON. Although Joe was right about today's topic being easy enough to enjoy the ambiance of a coffee shop, he has been doing quite a lot of coding this morning. He then takes a moment to think about how he'd write a unit test for that code. After another aha moment, now he's got it. Theo: The inputs of library.searchBooksByTitleJSON are library data and a query string, and the output is a JSON string. See Figure 6.4. So I would create a library data record with a single book and write tests with query strings that match the name of the book and ones that don't match. Joe: What about the expected results of the test cases? Theo: In cases where the query string matches, the expected result is a JSON string with the book info. In cases where the query string doesn't match, the expected result is a JSON string with an empty array. Joe: Theo: What? Joe: I don't like your answer. Theo: Why? Joe: Because your test case relies on a string comparison instead of a data comparison. Theo: What difference does it make? After all, the strings I'm comparing come from the serialization of data. Joe: It's inherently much more complex to compare JSON strings than it is to compare data. For example, two different strings might be the serialization of the same piece of data. Theo: Really? How? Joe: Take a look at these two strings. They are the serialization of the same data. They're different strings because the fields appear in a different order, but in fact, they serialize the same data. Joe turns his laptop to Theo. As Theo looks at the code, he realizes that, once again, Joe is correct. Tip: Avoid using a string comparison in unit tests for functions that deal with data. Theo: I see. Well, what can I do instead? Joe: Instead of comparing the output of library.searchBooksByTitleJSON with a string, you could deserialize the output and compare it to the expected data. Theo: What do you mean by deserialize a string? Joe: Deserializing a string S, for example, means to generate a piece of data whose serialization is S. Theo: Is there a Lodash function for string deserialization? Joe: Actually, there is a native JavaScript function for string deserialization. It's called json.parse. Joe retrieves his laptop and shows Theo an example of string deserialization. The code illustrates a common usage of JSON.parse. Theo: cool! Let me try writing a unit test for library.searchBooksByTitle.json using JSON.parse. It doesn't take Theo too much time to come up with a piece of code. Using his laptop, he inputs the unit test. Joe: well done! I think you're ready to move on to the last piece of the puzzle and write the unit test for catalog.searchBooksByTitle. Because Theo and Joe have been discussing unit tests for quite some time, he asks Joe if he would like another espresso. They call the waiter and order. Then Theo looks again at the code for catalog.searchBooksByTitle. Writing the unit test for catalog.searchBooksByTitle is a more pleasant experience for Theo than writing the unit test for library.searchBooksByTitle.json. He appreciates this for two reasons. It's not necessary to deserialize the output because the function returns data. It's not necessary to wrap the catalog data in a library data map. Joe: that's a good start. Theo: I thought I was done. What did I miss? Joe: you forgot to test cases where the query string is all lowercase. Theo: you're right. Let me quickly add one more test case. In less than a minute, Theo creates an additional test case and shows it to Joe. What a disappointment when Theo discovers that the test case with watchman in lowercase fails. Joe: don't be too upset, my friend. After all, the purpose of unit tests is to find bugs in the code so that you can fix them. Can you fix the code of catalog.data.searchBooksByTitle? Theo: sure. All I need to do is to lowercase both the query string and the book title before comparing them. I'd probably do something like this. After fixing the code of catalog.searchBooksByTitle, Theo runs all the test cases again. This time, all of them pass. What a relief. Joe: it's such a good feeling when all the test cases pass. Theo: sure is. Joe: I think we've written unit tests for all the search query code, so now we're ready to write unit tests for mutations. Thank goodness the waiter just brought our coffee orders. Section 6.4. Unit tests for mutations. Joe: before writing unit tests for the addMember mutation, let's draw the tree of function calls for system.addMember. Theo: I can do that. Theo takes a look at the code for the functions involved in the addMember mutation. He notices the code is spread over three classes: system, library, and user management. Theo grabs another napkin. Drawing the tree of function calls for system.addMember is now quite easy. See figure 6.5. Joe: excellent! So which functions of the tree should be unit tested for the addMember mutation? Theo: I think the functions we need to test are system.addMember, systemState.get, systemState.commit, library.addMember, and usermanagement.addMember. That right? Joe: you're totally right. Let's defer writing unit tests for functions that belong to system state until later. Those are generic functions that should be tested outside the context of a specific mutation. Let's assume for now that we've already written unit tests for the system state class. We're left with three functions: system.addMember, library.addMember, and usermanagement.addMember. Theo: in what order should we write the unit tests, bottom up or top down? Joe: let's start where the real meat is, in usermanagement.addMember. The two other functions are just wrappers. Theo: okay. Joe: writing a unit test for the main function of a mutation requires more effort than writing the test for a query. The reason is that a query returns a response based on the system data, whereas a mutation computes a new state of the system based on the current state of the system and some arguments. See figure 6.6. Tip: writing a unit test for the main function of a mutation requires more effort than for a query. Theo: it means that in the test cases of usermanagement.addMember, Both the input and the expected output are maps that describe the state of the system. Joe: exactly. Let's start with the simplest case, where the initial state of the system is empty. Theo: you mean that user management data passed to usermanagement.addMember is an empty map? Joe: yes. Once again, Theo places his hands over his laptop keyboard, thinks for a moment, and begins typing. He reminds himself that the code needs to add a member to an empty user management map, and to check that the resulting map is as expected. When he's finished, he shows his code to Joe. Joe: very nice. Keep going and write a test case when the initial state is not empty. Theo knows this requires a few more lines of code, but nothing complicated. When he finishes, he once again shows the code to Joe. Joe: awesome. Can you think of another test case for usermanagement.addMember? Theo: no. Joe: what about cases where the mutation fails? Theo: right. I always forget to think about negative test cases. I assume that relates to the fact that I'm an optimistic person. Tip: don't forget to include negative test cases in your unit tests. Joe: me too. The more I meditate, the more I'm able to focus on the positive side of life. Anyway, how would you write a test case where the mutation fails? Theo: I would pass to usermanagement.addMember a member that already exists in user management state before. Joe: and how would you check that the code behaves as expected in case of a failure? Theo: let me see. When a member already exists, usermanagement.addMember throws an exception. Therefore, what I need to do in my test case is to wrap the code in a try/catch block. Joe: sounds good to me. Once again, it doesn't require too much of an effort for Theo to create a new test case. When he's finished, he eagerly turns his laptop to Joe. Theo: now I think I'm ready to move forward and write unit tests for library.addMember and system.addMember. Joe: I agree with you. Please start with library.addMember. Theo: library.addMember is quite similar to usermanagement.addMember, so I guess I'll write similar test cases. Joe: in fact, that won't be required. As I told you when we wrote unit tests for a query, when you write a unit test for a function, you can assume that the functions down the tree work as expected. Theo: right, so I'll just write the test case for existing members. Joe: go for it. Theo starts with a copy and paste of the code from the usermanagement.addMember test case with the existing members in listing 6.23. After a few modifications, the unit test for library.addMember is ready. Joe: beautiful. Now we're ready for the last piece. Write a unit test for system.addMember. Before you start, could you please describe the input and the output of system.addMember? Theo takes another look at the code for system.addMember and hesitates. He's a bit confused. The function doesn't seem to return anything. Theo: the input of system.addMember is a system state instance and a member, but I'm not sure what the output of system.addMember is. Joe: in fact, system.addMember doesn't have any output. It belongs to this stateful part of our code that doesn't deal with data manipulation. Although DOP allows us to reduce the size of the stateful part of our code, it still exists. Here is how I visualize it. Joe calls the waiter to see if he can get more napkins. With that problem resolved, he draws the diagram in figure 6.7. Theo: then how do we validate that the code works as expected? Joe: we'll retrieve the system state after the code is executed and compare it to the expected value of the state. Theo: okay, I'll try to write the unit test. Joe: writing unit tests for stateful code is more complicated than for data manipulation code. It requires the calm of the office. Theo: then let's go back to the office. Waiter, check please. Theo picks up the tab, and he and Joe take the cable car back to Albatross. When they're back at the office, Theo starts coding the unit test for library.addMember. Theo, can we use _.isEqual with system state? Joe, definitely. The system state is a map like any other map. Tip. The system state is a map. Therefore, in the context of a test case, we can compare the system state after a mutation is executed to the expected system state using _.isEqual. Theo copies and pastes the code for library.addMember, listing 6.21, which initializes the data for the test. Then he passes a system state object that is initialized with library state before to system.addMember. Finally, to complete the test, he compares the system state after the mutation is executed with the expected value of the state. Joe, wow, I'm impressed. You did it. Congratulations. Theo, thank you. I'm so glad that in DOP most of our code deals with data manipulation. It's definitely more pleasant to write unit tests for stateless code that only deals with data manipulation. Joe, now that you know the basics of DOP, would you like to refactor the code of your Clapham prototype according to DOP principles? Theo, definitely. Nancy told me yesterday that Clapham is getting nice market traction. I'm supposed to have a meeting with her in a week or so about the next steps. Hopefully, she'll be willing to work with Albatross for the long term. Joe, exciting. Do you know what might influence Nancy's decision? Theo, our cost estimate, certainly, but I know she's in touch with other software companies. If we come up with a competitive proposal, I think we'll get the deal. Joe, I'm quite sure that after refactoring to DOP, features will take much less time to implement. That means you should be able to quote Nancy a lower total cost than the competition, right?